Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real honor to introduce our prestigious speaker, Sebastian Bubeck. Seb is the principal research manager of Machine Learning Foundation Group at Microsoft Research in Redmond, Washington. Prior to Microsoft Research, he was an assistant professor in the Department of Operations Research and Financial Engineering at Princeton. And he has made fundamental contributions to machine learning and optimization. He has received numerous prestigious awards, including the Sloan Research Fellowship in Computer Science and a Best Paper Award at Code, and Jacques Navier Prize for the Best French PhD thesis in Probability and Statistics. He was the general co-chair of Code 2013 and 2014 and serves on the steering committee for Code. He is also the author of the recent monograph, Convex Optimization, Algorithms and Complexity, which is published in 2015 as part of Foundations and Trends in Machine Learning. The title of his talk is A Law of Robustness for Two-Layer Neural Networks. Please join me in welcoming him.
Thank you very much for this very nice introduction. So I'm really thrilled to be here. It's a great pleasure to have accepted this invitation by Jing-Yuan Fang. You know, I know him since my very first day in Orphy a couple of years ago. Okay, so today I'm going to tell you about a project that I did last summer during pandemic summer 1. This is joint work with Yuanzhu Li and Dheeraj Nagaraj. Both of them are former intern of mine at Microsoft Research. Yuanzhu is now an assistant professor at CMU, and Dheeraj is a graduate student at MIT. So as I have mentioned just prior to the introduction, this is going to be a mathematical talk. So you should really interrupt me if there is something which is not clear, because each slide builds on the previous one. So if you're lost at some point, it might be difficult to catch up later on. So please, interrupt me with questions or ask questions in the chat. Okay, so let's get started. So the premise or the context for this work is the following sentence: adversarial examples are a problem. Okay, so I hope I don't need to define adversarial examples to this audience. By now, everybody, I think, is aware of this phenomenon. So let me just repeat it very succinctly. The problem is that modern neural networks, like all the modern ones, every state-of-the-art neural network has a big problem, which is that you can find tiny perturbations of the input that will completely change the output. So Alexander Madry likes to say that modern neural networks can make pigs fly. And what he means by that is you show an image of a pig and you apply a tiny perturbation to this image of a pig. And, it still looks like a pig to you, to a human, but suddenly the computer, the neural network will say that it's an airplane. Okay, so that doesn't make any sense. And we would like to resolve this problem. So that's the context. Now, as I said, we're going to be doing a mathematical talk. So mathematically, the way I interpret this problem of sensitivity to tiny perturbation is that the neural network is computing a very non-Lipschitz function. And what we want to ask is, why is that? Why are these modern neural networks very non-Lipschitz? Okay. And more specifically, I want to propose that maybe there could be some high-dimensional phenomena, like a high-dimensional geometric phenomenon, that could explain why it's actually hard in high dimension to get a Lipschitz function that fits, training data. So I already give away this fitting of training data. So we're going to be talking about memorization in this presentation. So as I write here, we want to understand why we have not been able to train smooth memorization machines. So smooth, okay, we all understand smooth means Lipschitz. And memorization machine, by that I mean our neural network, we're going to view it as a way to fully memorize training data. And this is consistent with current practice where we always train to zero training error. We always perfectly fit the data. Now, this view of neural network as simply memorization machines is restrictive. And many of you probably in the audience are thinking about or are aware of, these other properties of neural networks, such as generalization. Not only is it good on the training data, but it's also good on data that it has not seen. We're not going to be talking about generalization in this presentation. Everything is going to be focused on the memorization part. Okay, and this is restrictive, and it would be a different presentation to talk about generalization. Now, what is the upshot of the presentation? What I'm going to try to tell you, or conjecture, as you will see, we cannot fully prove it. I'm going to conjecture and tentatively prove that actually memorizing smoothly is much, much, much harder than just memorizing. Okay, and by what I mean by much, much harder, by that I mean that you need a much bigger model. And you will see that it's not going to be like you need a 2 times or 3 times bigger model to smoothly memorize. It will be that you need a D times bigger model, where D is the ambient dimension. So, if you have images which are like, I don't know, like high res images, which are 1 million dimensions, then you need a 1 million times bigger neural network to smoothly memorize compared to just memorization. Okay, so that I think is a pretty striking phenomenon, and again, it's going to be mostly a conjecture. We cannot fully prove it. So let's get started into the more formal part to explain the conjecture precisely and what I mean. So we're going to be talking about memorization. What is a memorization task? So given some function class script f, think of neural networks, of parameterized models, and a data set which consists of pairs, input output, so xi, yi. The xi's are d-dimensional vectors, the yi are real outputs. What is the memorization task? So we're going to have n samples like this. The memorization task is to find a model in your function class which memorizes the data, namely when you ask f what is the value at xi, it returns yi. And everything I say, instead of exactly equal, it could be approximately equal, but just to clarify, we're going to be talking about exact memorization, but this is really irrelevant. It doesn't matter. Now we're going to focus on a very specific function class, which is the function class of one hidden layer neural network, described as follows. So you fix an activation function psi from the real line to the real line. Think, for instance, the rectified linear unit, so the positive part of a real number. Now the function class script f sub k of psi is the set of one hidden layer neural network with k neurons. What are these functions? These are the following functions. So you're going to have a vector WL in RD. Okay, you're going to have k vectors like this. Now, what does the else neuron compute? The else neuron computes this linear function, WL.x. And then, so it computes the linear function WL.x. Then it applies the nonlinearity psi. So psi of WL.x. This is the output of the else neuron. Now I have k neurons, and all these outputs are recombined linearly with coefficients AL. So any function which can be written like this for some set of AL and some set of WL, this is in my function class. Now, why is this function class important? It's important because it's arguably the simplest universal class. By universal, I mean that as long as the activation function is not a polynomial, for any memorization task, if k is large enough, you can satisfy the memorization task. Okay, so you can always interpolate. You can interpolate any data with this function class. It's a universal function class. In fact, you can approximate any continuous function. Okay, so we're going to be focusing on this function class. Now, of course, I said that you need k to be large enough, okay, for the memorization task to be satisfied. Now, a very natural question is, how big of a k do you need? And this was already answered, more than 30 years ago. So here is a theorem. This is an important theorem, and we're going to prove it together on the next slide. It's very, very simple. So let's take psi again to be not a polynomial, and in this case, it's just a step function. Okay, so it's 0, and then it jumps to 1. So with this step function nonlinearity, for data in general position, what does data in general position mean? It just means that there is no spurious linear correlation between the covariates between the xi. To put it differently, if I look at a subspace in RD, then a subspace is going to contain at most d points. Okay, there won't be like d plus 1 or d plus 2 points on a subspace. There will be at most d points on a subspace. Okay, so this is data in general position. It's not really an assumption, just to be clear. Okay, we're going to make real assumptions soon, but data in general position is not an assumption. You can apply, infinitesimal noise and everything will be in general position. Okay, so this is not really an assumption. And let's say we have binary labels. Okay, so the yi's are, let's say, 0 and 1. Then what Eric Baum proved in 1988 is that the number of neurons that you need is twice the number of data points divided by the dimension. If you have that many neurons, then you can achieve the memorization task, always. Now, how do you interpret this bound, k larger than 2n over d? Well, really what matters is k times d, because you see the number of parameters you need to describe a one hidden layer neural network with k neurons is roughly k times d. For each neuron, you need d plus 1 parameter, d parameter for the WL and 1 parameter for the coefficient AL. So it's parameterized by, the number of parameters is k times d plus 1. So all this theorem is saying is that you basically need number of parameters larger than number of equations, right? F of xi equals yi for any I in 1 through n. These are n equations. So all you're saying is you need number of parameters larger than number of equations, which totally makes sense. Okay. Now let me just briefly mention these works do much more than just this, but maybe you're not happy about the binary labels, maybe you're not happy about the step function. So in those papers, what we proved is that if you use a rectified linear unit, then actually you can fit arbitrary real labels, and all you need is to replace this factor 2 by a factor 4. Okay, and I will explain this also on the next slide. Okay, so because of the importance of this theorem for the next of the discussion, for the rest of the discussion, I'm going to prove it to you right now, and you will see it's really trivial. Okay, so how does the proof go? Well, the first thing to realize is that with a step function, you can, with using just 2 neurons, you can build the indicator of a slab. What is a slab? You take a subspace w dot x equal t. Okay, so you have a direction w, and you go at distance t in this direction, and this is your subspace w dot x equal t. Now you want to build an indicator of a slab, so a little, enlargement of this subspace, and you can do this just by taking the difference of those 2 neurons. The indicator of w dot x is larger than t minus epsilon, minus the indicator of w dot x is larger than t plus epsilon. Because you see, if I go in the direction w, I will first hit t minus epsilon. At this point, this neuron is going to start firing, but this neuron is still not firing because I'm at t minus epsilon, not yet t plus epsilon. And if I go a little bit further, then I reach t plus epsilon, and at that point, these neurons start to fire, and so they cancel each other. 1 minus 1 equals 0. Okay, so it's 0 before the slab, it's 0 after the slab, and it's 1 inside the slab. Okay, so just 2 neurons give me the indicator of a slab. Now, how am I going to use this gadget to interpolate arbitrary data? The way I will do it is like this. Recall that the data is in general position. So what happens is that I can take a group of d points with the same label, let's say plus 1. So these are those crosses here. Now I can put them on a subspace because it's d points, so that they satisfy a linear constraint that they are on a subspace. And because it's in general position, I know that there is a little slab. I can enlarge this subspace so that it still does not contain any other data points. Okay, so this green region, the slab, is thin enough so that it does not contain any other data point. And I know that there exists a weight small enough that does not contain any other data point because the data is in general position. Now, what I can do is that I can use 2 neurons to just build the indicator of this green region. So the indicator of this green region is going to give me the correct label on these d points, and it's just going to give 0 on all the other points. So I can keep doing that. You see, I can keep doing that. And eventually I'm going to cover all my points, and all my points will have the correct label. And you see, I only used 2 neurons for d points. So in total, for n points, I only need 2n over d neurons. And that's it. Okay, that completes the proof. Is that clear? Is there any question on this proof?
Yes.
Yeah?
Yeah.
Go ahead. Is there a question?
No.
No. Okay. 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 So I mean, I think it's a really trivial proof. So I'm glad nobody has a question. Now, with the rectified linear unit, you can in fact do more, because in this lab, instead of doing the indicator of this lab, you can actually do a linear function. Why is that? You can just use the fact that the derivative of the rectified linear unit is a step function. Now, in high dimension, because really a neuron with the ReLU is the ReLU composed with a linear function, so the derivative, the gradient, is going to be a linear function times the derivative of ReLU. So you're going to have, like, with two neurons, with two ReLU neurons, you can build an indicator, a step function like this, times the linear function. So what this means is that instead of doing the indicator of the slab, you can build a linear function in the slab. So you can actually interpolate any arbitrary label in the slab, and you have just used twice as many neurons. Okay, so good. All right, so this, we're going to refer to it as bound construction. Now, of course, anybody doing machine learning, should scream out of his lungs that this is a terrible, terrible construction. It's like it's not going to generalize anything. This is the epitome of overfitting, right? It really just narrowly fits the data, and as soon as something which is not in the data set, it says 0. Okay, so this is really a terrible construction. Now, as I said, I don't want to talk about generalization in this presentation. So for us, we're going to view this as a bad construction because it's very non-Lipschitz. You see, it drops from 0 to 1 very quickly. Now, of course, you might say, Seb, of course it drops to 0 to 1 very quickly. It's using a step function, which is very, very non-Lipschitz. But, forget about that. This is not really the point. Like, instead of a step function, think about, maybe I do a small linear slope between the 0 and the 1 so that it's a constant Lipschitz, the activation function, and I can do the exact same calculation as what I did. Okay, so the fact that it's a step function is not the problem. The problem is that really you needed to have a very thin slab so that you don't catch any other data point. So now let's try to be a bit more concrete and ask exactly, okay, what is actually the Lipschitz constant? And to answer this question, we're going to need some model of the data, because if you just say the model is in, is in general positions, this is not going to say anything. Like, it could be arbitrarily bad. So the model of data that we're going to use in this presentation for the rest of the presentation is that of well-dispersed data. And instead of, formalizing what I mean by well-dispersed to fix idea, and because this is anyway not the main point of the presentation, let's just say we're going to work with covariates, the xi's, which are IID on the sphere. Okay, so they are just uniformly distributed unit norm vectors. Okay, this is a very simple model. Now, what happens if I do the bound construction for such well-dispersed data, for IID data on the sphere? Well, you see I have this green slab, and it's very easy to see that what happens is I have the direction W along which the slab is. It's a simple calculation to see that all those points, they are a distance 1 over square root D in this direction. Okay, so you fitted D data points on a hyperplane. Now, what it means, because those points are randomly distributed, it means that in this direction they are distance 1 over square root D. But now here is the key observation. Actually, all the data is within a band of width 1 over square root D, right? Because if I look at any fixed direction, a random point, its inner product with a fixed direction is going to be 1 over square root D. So all the data is in a narrow band of width 1 over square root D. So what does it mean? It means that certainly the green band needs to have a width which is smaller than 1 over square root D. Okay, maybe much smaller than 1 over square root D. So in other words, as I just said, the slab, the green slab, if I don't want it to contain any other data point, it will need to have a width much smaller than 1 over square root D. So the Lipschitz constant will be at least square root D, because I move, from 0 outside of the slab to 1, let's say in the center of the slab. So I move from 0 to 1 in distance 1 over square root D. So this gives me square root D Lipschitz. Okay, and square root D Lipschitz, of course, we're going to say this is bad. Okay, it's a large number. It's very non-smooth. It varies very, very quickly. Now, let me just say, this is the next point I'm going to make is not too important to follow the rest, but I want to be precise, and it's somewhat important for people who want to work on the conjecture. So the Lipschitz constant is in fact worse than square root D. It is as bad as D. So let me explain why. So you see, when I move this is one neuron direction, okay, this one. So when I move in this one neuron direction, I can move by distance 1 over square root d, and I will activate this neuron. But I have only moved distance 1 over square root d. Now I can move distance 1 over square root d in another neuron. Now all the neurons, it's easy to see that they are roughly orthogonal, okay, because they are basically random direction. So I move 1 over square root d in the direction of the first neuron, 1 over square root d in the direction of the second neuron, and so on and so forth. Eventually, I can activate, you know, of order of d neurons, because I can move 1 over square root d for d times, and I will only have moved of order of 1, because the distance is the sum of the square, right? So I move 1 over square root d squared plus 1 over square root d squared, etc. I moved in total the sum of 1 over square root d squared d times, so that gives me 1. So I have moved distance 1, and I have activated d neurons. So by moving distance 1, I went from 0 to d. So this tells me that I'm at least, in fact, d Lipschitz. And you can prove that this is tight. Okay, this is the worst case. Okay, so let me just recap. So the Baum construction, it's using only k, the number of neurons, to be of order n over d. But it is, let's say, optimistically square root d Lipschitz for well-dispersed data. In fact, it's even worse. We just saw that it's, in fact, d Lipschitz, but let's not worry about this too much. Now, the key point is that for these well-dispersed data, you can actually be constant Lipschitz. Okay, so again, here is another assumption we're going to make for the rest of the talk, that n is polynomial in D. Okay, so if you have polynomially many uniform points on a sphere, then all those points are isolated. They are all far from each other, right? Let's say if you have D to the 5 points, then they are all at distance 1 over 10 from each other. Okay, like literally 1 over 10 with like super high probability. So it's very easy to have a constant Lipschitz interpolation. You can build something like this. So again, I have my data points, let's say D to the 5 data points, and they are all separated, meaning that if I look at one point, then in a ball of radius 1 over 10 around it, I don't see any other data points. So what I could do is that I could just interpolate with a bump function. Okay, so you remember a bump function, it's a technical term, which means basically you go from 0 to 1 in a C infinity way on a compact set. Okay, so it's like, you know, it's very smooth. It's like 10 smooth, 10 Lipschitz, and goes from 0 to 1. So you see this little red gadget here is just giving me the correct label at the center, which is this data point, and it gives me 0 on all the other points. It does not affect any of the other points. Okay, now, so this, you know, I can just add a bunch of bumps like this, and this shows that you can be constant Lipschitz and interpolate, you know, random data on the sphere. Now, in fact, you can do this with neural networks. It's very easy to see, it's very believable that you only need of order of n neurons to do a similar construction. You just need a constant number of neurons to approximate this red bump. In fact, you literally need 1 neuron per data point to do something like a bump like this on the sphere. Okay, but this doesn't matter too much. The point is, by using many more neurons than the Baum construction, you can be Lipschitz. So let me summarize the discussion so far. So this is the most important part. So far, what we've seen, we have 2 options. Either we have a small model of size k of order n over d, but it's very non-robust. It's square root d Lipschitz, in fact, even worse. Or the other option that we've seen is you have a very large model where k is the number of neurons is of order of the number of data points, and this one is very robust. And of course, very naturally, the question is this trade-off real? Can we do better? You know, could we get the best of both worlds? Could we get a small model, which is also smooth? Okay. And of course, we conjecture that this trade-off is real. Okay, so we conjecture what we call a law of robustness, namely that smooth memorization requires overparametrization by a factor d compared to mere memorization. And in fact, we conjecture an entire trade-off curve between the number of neurons that you're going to use and the smoothness that you can attain. Namely, here is the conjecture. The conjecture is that for well-dispersed data on the sphere, again, think just IID covariates xi on the sphere. there exists a target binary label function yi. In fact, we believe it's true for most labels, but never mind that, with the following property. So for this data set, for this random data set, it has a property that any one hidden layer neural network using K neurons that memorizes the data must also have its Lipschitz constant larger than a constant times square root n over k. Okay, this is a conjecture. You know, let me already say we don't know how to prove it. This is still open. You know, if you want to drop from the call now and try to prove it, you're more than welcome to do it. What I'm going to do next is I will tell you what we know about it. We have proved some things around it, but you know, we don't know really how to prove it. So let me just make sure we're all on the same page. So far, we've discussed two regimes, but only upper bound, not lower bounds. One of them is the optimal size regime, okay, which is this Baum construction, where k is of order n over d. You cannot do better than you know, you cannot do a smaller neural network than this, just information theoretically, if you want to satisfy n equations. In that case, if you use k of order n over d, the conjecture implies that the Lipschitz constant will be at least square root d. Okay, so that's interesting. And on the other hand, you can look at what the conjecture will say if you assume that you have memorized with a Lipschitz constant smaller than 1 or of order constant, then the conjecture says that k needs to be n. Okay, so you see already in those two extremes that the conjecture exactly tells us that the previous slide was optimal. Let me say with the caveat that from the upper bound perspective, the Baum construction does not actually give you square root d when k is n over d, it only gives you d. In fact, you can play with the parameters and you can see that you can do a Baum construction with k neurons and the Lipschitz constant is going to be n over k. Okay, so you see n over k is bigger than square root n over k. And in fact, it's pretty striking, but even finding a matching upper bound for this law of robustness is not an easy task. And towards the end of the presentation, we'll discuss some progress towards a matching upper bound. But let me pause here for a minute and see if there are questions on the conjecture or what we discussed so far. No question at all?
Right, it's very clear. Yeah.
Okay, that's great to hear. Okay, so I will just keep going, and you know, I'm gonna tell you what we know about this conjecture. So what do we know? So we tried 3 different approaches to prove it. We tried a geometric approach, a statistical approach, and an algebraic approach. And each one of them gives something somewhat interesting, but they all fall short of the real goal. So the first approach, geometric, I will tell you, I will give you the proof on the next slide. Maybe I will just go over it rather quickly. But what it gives is the following. It gives a lower bound of square root d over k instead of square root n over k. Now, let me bring your attention to the fact that square root d over k is much weaker than square root n over k. Why do I say it's much weaker? I say it's much weaker because it only says something interesting. Recall that you only say an interesting lower bound if you prove a lower bound bigger than 1. Because of course you need to be at least 1 Lipschitz if you want to be on the sphere and interpolate points that can change value from -1 to +1. Okay, so of course you need to be at least 1 Lipschitz or you know even 10 Lipschitz. So it's only interesting if you can prove a lower bound which is growing to infinity, let's say, in certain parameter regime. So you see square root d over k. This is only going to be interesting when k is the number of neurons is less than d, which you can think about as an undercomplete regime, where your neurons don't even span the entire space. Okay, so when you don't even span the entire space, then something else happens. Like you're just, you will see, I will explain on the next slide. Okay, so this gives you a weaker lower bound. Now, the next approach that we tried is the statistical approach, and I'm going to give you the full proof of the statistical approach on this slide. So it goes like this. So we can prove the following lower bound, where we replace the true Lipschitz constant by a proxy for it. Namely, look at this as follows. So one hidden layer neural network, you can think about it as a linear function, the output layer A, composed with the activation function psi, which is applied coordinate-wise to Wx, where W is a matrix of the first hidden layer. Okay, it has the rows which are given by the WL from the previous notation. Okay, so this is a perfectly correct way to write a one hidden layer neural network. So it's a composition of the linear function A, the nonlinearity psi, and the linear operator W. So the Lipschitz constant of F by the chain rule is upper bounded by the product of the Lipschitz constant of all these elements, namely the Lipschitz constant of psi times the Lipschitz constant of the linear function A, which is the Euclidean norm of A, times the Lipschitz constant of the operator W, which is the operator norm of W. Okay, the spectral norm of W. All right. So what I'm going to do for you now is that I'm going to show you that the conjecture is true for this quantity, namely the product of the Lipschitz constant of psi times the L2 norm of A times the operator norm of W. This is indeed lower bounded by square root n over k. But notice that it's only an upper bound. Okay, I'm proving a lower bound on an upper bound. So it's not saying anything about the real Lipschitz constant. And indeed, the whole difficulty is about showing that there isn't a construction where there are crazy cancellation. And if you look at, this quantity is large, but actually the real Lipschitz constant exhibits so many cancellations that the real Lipschitz constant is much smaller. Okay, this is really the difficulty. But in any case, it's still a natural quantity, this product of things, which is also called the Baron norm of your neural network. Anyways, that doesn't matter too much. And the way we're going to prove a lower bound is that we're going to relate it to the Rademacher complexity. So we're going to, in fact, relate it to generalization. And we're going to show that, if you interpolate random data, then you cannot generalize. So your Rademacher complexity will have to be large. So this quantity will have to be large. So let's do it. It cannot be complicated. Everything is going to be on this slide. So let me remind you the Rademacher complexity for a function class script f. It's the expected supremum of how well you can correlate with random data. So let's say the yi are random signs, random plus 1 minus 1. You just take the sum for I equals 1 to n of yi f of xi. And you look at how well you can match the f of xi with those random signs. And you rescale by 1 over square root n. Okay, so this is a very natural quantity. I don't want to dwell on it too much. I hope everybody is familiar with it. So let's look at this sequence of inequality. So the first inequality, the Rademacher complexity of one hidden layer neural network is upper bounded by the Lipschitz constant of psi times the sum of the product of the absolute value of AL times the Euclidean norm of WL. So this is, in machine learning 101 class, everybody should have seen this. This is just the standard upper bound on the Rademacher complexity of one hidden layer neural network. If you want to prove it, it's just the fact that you can use Talagrand contraction lemma, which will bring out the Lipschitz constant of psi, and then you're left with the Rademacher complexity of a linear model, and the Rademacher complexity of a linear model is the L2 norm of this linear model. So that's why you have the L2 norm of WL that appears. Okay, so we get the sum of this product. Now recall what we want is the Euclidean norm of A times the operator norm of W. So suddenly I can do a Cauchy-Schwarz, and I will get that the sum of those products is smaller than square root of the sum of those things squared times the sum of those things squared. Now, square root of the sum of the AL squared, that is the L2 norm of A. And square root of the Euclidean norm of the WL squared, that is the Frobenius norm of W. It's the sum of the, it's square root of the sum of the square of all the elements of W. Okay? So I get that this quantity is upper bounded by the L2 norm of A times the Frobenius norm of W. But now I want to make appear the operator norm of W. And for this, I'm going to have one more inequality, which we're going to use several times again in the next slide. So I want to dwell on it for a minute. We're going to use the fact that the Frobenius norm is upper bounded by square root of the rank times the operator norm. And the rank of W, because I have only k neurons, it's a k by d matrix, the rank is only k. So I can upper bound the Frobenius norm of W by square root k times the operator norm of W. Now, let me remind you, why is it true that the Frobenius norm of, let's say, a symmetric matrix is upper bounded by square root of the rank times the operator norm? Well, it's because I have the magic of eigenvalue decomposition. The Frobenius norm is also the L2 norm of the spectrum. The Frobenius norm is also square root of the sum of the eigenvalue squared. So, sum of the eigenvalue squared, it's upper bounded by the number of non-zero eigenvalues, which is a rank, times the largest eigenvalue squared, and square root of the largest eigenvalue squared, that's the operator norm. So that's why I get the Frobenius norm is smaller than square root rank times the operator norm. It's because of eigen decomposition. Okay, but now see what we did. We did exactly that. The Rademacher complexity is upper bounded by square root k times the Lipschitz constant of psi times the L2 norm of A times the operator norm of W. But the Rademacher complexity is larger than square root n because I assume that I can memorize. So if I can memorize that, I can match my f of xi to be yi. So yi times yi, it's yi squared, it's plus 1. So this sum is n. So n over square root n, I get square root n. So because I can memorize the Rademacher complexity is at least square root n, so this sequence of inequality exactly tells me Lipschitz constant of psi times L2 norm of A times operator norm of W is lower bounded by square root n over square root k. Okay, that's it. All right, so this gives you a complete, perfectly formal and valid proof of the law of robustness, but not for the Lipschitz constant, but for an upper bound on the Lipschitz constant. But you see that it's missing the point. You don't care about this upper bound on the Lipschitz constant. You care about the real Lipschitz constant. Okay, so this is all I will say about the statistical approach, and this is all that it gives us. Now, actually, the deepest part of our work is the algebraic approach. So the algebraic approach is, we're going to assume that we have a polynomial activation function, a degree p polynomial. Now, if you remember on the very first slide, I said, let's assume that psi, the activation function, is not a polynomial. You need it to be a non-polynomial if you want to have universality, if you want to be able to approximate any function. Now, with a polynomial, you cannot approximate any function, but you can still do a lot. Namely, with a degree p polynomial, you can still memorize of order of d to the p points. Okay, so you can memorize many points. So with a quadratic, you can memorize d squared points, but you cannot do d cubed. Okay, but you can do d squared. And in that case, we prove the actual real law of robustness. So square root n over k, not in the undercomplete regime, not an upper bound on the Lipschitz constant, the true Lipschitz constant. So we prove the true law of robustness, but only in what we call the max rank case, which is, let's assume n is d to the p. In this case, the optimal size regime is k is n over d, and k is n over d. That means k is d to the p minus 1. And this will correspond to a certain tensor. I will explain in 2 slides what this tensor is. This corresponds to a certain tensor being max rank. And in this case, we prove the law of robustness. Okay, so I'm going to explain, this is the deepest part of the work and the most interesting technically, and I will explain this a little bit more. Okay, so now the plan is, next slide, I do the geometric proof. I go over it very quickly, and then we're going to spend a little bit more time on the algebraic approach and the connection with tensors. Any questions there?
No.
All right. Okay, so let's do the geometric proof. So the geometric proof is actually very, very simple. And why is it so simple? It's because it applies to a much more general model than just one hidden layer neural networks. Namely, it applies to what's called multi-index model. So you remember in economics, a single index model is when you have maybe a high dimensional data, but all your decisions, you're going to make them based on just one indicator, meaning the projection on a single direction. That's a single index model. Now, a multi-index model is when you make your decision based on the projection on k direction. So you have a subspace, a k-dimensional subspace. Let's denote by p the projection on this k-dimensional subspace. A multi-index model is a function f of x, which is in fact a function g of p of x. Okay, so it only depends on the projection on this k-dimensional subspace. Now, of course, of k neurons, one hidden layer neural network is a multi-index model with k indices, which are the k neurons. Okay. Now, the claim is that if you have a multi-index model like this, and it memorizes random data on the sphere, then it must be that the Lipschitz constant is larger than square root d over k. Okay. So this proves the geometric statement that I made. So let's see why this is true. And rather than doing the proof, I will just say it in words. It's very, very simple. The point is you have this sphere, which is of radius 1, and you're going to project it on a k-dimensional subspace. When you project, the sphere is going to shrink. Just think about projecting on a single direction. If I project on a single direction, then most of the points on the sphere, they are projected on the width, on an interval of width 1 over square root d. That's already what we talked about before, right? If I fix a direction, then most of the mass is in an interval of 1 over square root d. If I do it over 2 directions, then I'm going to have 1 over square root d plus 1 over square root d. And if I do it on k direction, in fact, it's square root of the sum of the squares. So square root of the sum of the 1 over d, and I have this k times. So if I have a k-dimensional subspace, everything is in fact in a ball of radius square root k over d. And just to be clear, when I say everything, I don't literally mean everything, but I mean most of the mass, like, except an exponentially small fraction of the mass, most of the mass is projected in a much smaller amount of space. So again, I have my sphere of radius 1. And now it becomes a sphere basically of radius square root k over d. But on this sphere, I need to move from -1 to +1. So in space square root k over d, I move from -1 to +1. So I need to be at least square root d over k Lipschitz. And that's it. That's the proof. Now there is a small catch, which is that the k-dimensional subspace that you choose, of course, you choose it depending on the training points that you've seen. So, it's not like there is a dependency between the subspace and the point on which you're going to test your hypothesis. So you need to deal with this dependency. And, this is what's done here in the second part, tiny difficulty dependency between P and the direction in the data set. And you can do just a simple averaging argument. I'm going to skip this because it's really just an exercise. Yeah, it's really just an exercise. It's easy to do. But you see, it's really not capturing at all what we're talking about because it applies to these multi-index models. And notice that, of course, for multi-index models, square root d over k is the best you can hope for because when k is equal to d, you're not making any assumption, right? A multi-index model with d indices, it's any function. And we know that there exist functions which are constant Lipschitz. So this bound is the best you can do for multi-index models. Okay. All right. Okay, so now we're going to move to the, again, as I said, the deeper part of the work, which is the algebraic approach. And we're going to start, so we're going to have, I think, 2 slides on this, actually 3 slides. So this slide is a warm-up with just a quadratic network. Next slide is a general polynomial of degree 3, where we're going to have tensors. And I will then have a 3rd slide where I use this tensor construction to prove the upper bound, a matching upper bound, and then we will conclude with open problems. Okay, so this is the plan for the next 15 minutes. Okay, so let's do the warm-up with a quadratic network. So let's say that our activation function is t squared. As we said, with t squared, you have only d squared degrees of freedom. So you're only going to be able to fit d squared data points, just as a disclaimer. So when you use this activation function, what does the function look like? It looks like the sum of AL psi of WL dot x, which is the sum of AL WL dot x squared. Now this is a quadratic function in x, so I can represent it in matrix notation. There is some underlying matrix sigma, such that this function, this quadratic function in x, is nothing but the inner product, the Hilbert-Schmidt inner product over matrices between sigma and XX transpose, right? Which, is just the trace of sigma XX transpose, and because the trace is commutative, it's the trace of X transpose sigma X, okay? And this is a real number, so it's just the trace of a real number is a real number. So this thing here is just X transpose sigma X, which is a quadratic function. And it's very easy to see what is sigma. Sigma is nothing but the sum of AL WL WL transpose. Okay, so again, let me just recap what we just did. We just saw that one hidden layer neural network with a quadratic activation function, it's just a quadratic form, whereas the underlying matrix is the sum of AL, WL, WL transpose, whereas the AL are the linear coefficient that you use to recombine, and the WLs are the neurons. Now, it's very easy to see that this quadratic form, its Lipschitz constant on the sphere, is nothing but the operator norm of the underlying matrix. So all we need to do is to say that if you have a quadratic form that interpolates data on the sphere, then its operator norm must be large. That's what we're going to do. And the insight is just one sentence. It's always just one sentence. The insight is the following. For polynomial network, we'll see that memorization implies that the network, when I say the network, I mean the underlying matrix that represents it, or in general, for more general polynomials, the underlying tensors that represents it. So the network, let's say sigma in this case, will have to correlate with a small random quantity. We'll see what this small random quantity is. And so if you correlate with something small, then you must be big. And so that's how we're going to prove a lower bound on the operator norm. We're going to say the underlying network correlates with a small random quantity, so it's big, so the operator norm is going to be lower bound. So let's see how to do this very concretely. Let me denote omega, the following matrix, the sum for I equals 1 to n of yi, xi, xi transpose. I want you to think of this, let's say the yi's are random sign. I want you to think of this as a random walk over rank 1 matrices. I have these rank 1 matrices, x1, x1 transpose, x2, x2 transpose. And what I do is either I do plus x1, x1 transpose or minus x1, x1 transpose. Then I get the next one rank matrix, and I do either plus x2, x2 transpose or minus x1, x1, x2, x2 transpose. And I keep going like this. I do this random walk over rank 1 matrices. Because it's a random walk, you can imagine that there is going to be a lot of cancellations. So you can imagine that this omega is going to be small, and we're going to see what small means. Now, it is small, but sigma, the matrix representing the network, must correlate with omega. Why is that? Let's take the inner product between sigma and omega. By linearity, it's just the sum of the yi times the inner product between sigma and xi transpose. But sigma memorizes. So sigma times xi transpose is yi. So sigma times omega, it's the sum of the yi squared, which is n. So we see that sigma correlates very well with omega, namely its inner product is n. Okay. Now I want to say that omega is small, and that will mean that sigma will be large. How do I witness this? Well, I can just apply Hölder's inequality. I can pick any pair of dual norms. Think, for instance, the Frobenius norm, and the dual norm of the Frobenius norm is the Frobenius norm. But you can pick other pairs. So the inner product between sigma and omega by Hölder's inequality, or by definition of a dual norm, this is upper bounded by the norm of sigma times the dual norm of omega. Now, if omega is small, but the product of those two things is larger than n, this means that sigma is large. This is how we're going to prove it. So let's execute this strategy by using the Frobenius norm. So if you use the Frobenius norm, it's a very, very easy calculation to see that the Frobenius norm of omega is only square root n. Okay, so the Frobenius norm squared is only n. This is a calculation everybody can do in a minute. So you see, this is the cancellation I was talking about. Because it's a random walk, it's only going to have deviation of order square root n. Okay, so the Frobenius norm of omega is square root n. So that means, because the product of the Frobenius norm of sigma times the Frobenius norm of omega is larger than n, that means that the Frobenius norm of sigma is larger than square root n. And now again, I'm going to use what I told you on the slide before, namely that the Frobenius norm is upper bounded by square root of the rank times the operator norm. So the Frobenius norm is upper bounded by square root k times the operator norm of sigma. So that means that the operator norm of sigma is larger than square root n over k. That's it. We just proved right now the law of robustness for quadratic network, just using this very, very simple tactic. Any question on this proof?
So it's very clear. Yeah,
it's very clear. Very good. So now here, I will say one more sentence on this slide, which is actually an important sentence in terms of future open problems. Namely, you can prove an even stronger lower bound. So not only the law of robustness is true, but an even stronger lower bound is true. So by studying the operator norm of omega instead of studying the Frobenius norm and playing a little bit, what you will see is that the operator norm of sigma is in fact lower bounded by square root n over k times square root d over k. Okay, and k, of course, the number of neurons, because it's a matrix, I cannot have more than d neurons, right? The rank is always going to be at most d. So I can have at most d neurons, so square root d over k is a factor which is bigger than 1. Now, the way to interpret this is saying that if you use a low rank quadratic network, then it's not even going to be able to match the law of robustness. It's going to be provably worse than the best you could possibly attain in terms of Lipschitzness. So in a way, it's saying if you're using a too simple model, then you're missing out and you're not going to be able to extract everything you can from the law of robustness. I will come back to this, but just, you know, it's just a stronger inequality, right? You see that it's saying that you should never, basically it's saying, if you care about robustness, you should never use a low rank quadratic network. Because if you use a low rank quadratic network, probably you're not going to be the best that you can possibly do. Okay, so now let's move on to tensors. Maybe I will go rather quickly over tensors. So let's see. So now let's say that our activation is t to the p. Then my network is a sum of ALWL.x to the p. Now, just like before, you know, before it was a quadratic form, now it's a degree p polynomial in p, and you can represent it as some tensor t times the tensor product of x p times. So xx transpose, this is a tensor product of x 2 times. Now you have the tensor product of x p times. Maybe I don't want to, if you don't know this notation, you can check the YouTube videos that I have on a crash course for tensors. Maybe I don't want to explain too much about it right now. But the point is, your network is now represented by a tensor, which is a sum of ALWL tensor p times. And you can repeat the exact same argument as before. Instead of having a random walk over rank 1 matrices, you're going to have a random walk over rank 1 tensors. And as before, n is smaller, than some norm of t times the Frobenius norm, not Frobenius norm, times the dual norm of omega. Now, here is the problem. Here is the beauty and the difficulty. Before, remember, we crucially used that there is a relation between the Frobenius norm, the rank, and the operator norm. Namely, we use that for matrices, the Frobenius norm is smaller than square root of the rank times the operator norm. But this is false for tensor. This inequality is not true. And a very, very beautiful counterexample is a matrix multiplication tensor. I don't have time to explain in more detail what this means, but I can maybe in the Q&A, if you want to ask me, I can answer this. Now, what is true is the max rank version. Namely, it is true for tensors that the Frobenius norm of a tensor is smaller than square root of d to the p minus 1 times the operator norm. And d to the p minus 1 is the maximal possible rank of a tensor of rank p, okay, of order p. Sorry, not rank, of order p. Okay, when p is equal to 2, the max rank is d to the 2 minus 1, so d. A 3 tensor, it's d squared. A 4 tensor is d cubed, etc. So you see that we're going to be able to repeat the previous argument in the max rank case when k is like d to the p minus 1. So that's it. Okay, this is a proof for tensors in the max rank case. It's not that difficult. Now, quickly, let me talk about upper bounds. So recall that Baum's construction, in fact, only gives us a Lipschitz constant of n over k. It does not give us an upper bound of square root n over k. Now I'm going to give you a tensor construction that gives you square root n over k, but only in a specific regime. So let's assume that n is again epsilon to the d to the p. Okay, so that means that I can fit possibly with an activation function psi of t equals t to the p. Now let's consider the network, which is given by the tensor sum of yi xi tensor p times. Now notice this tensor, naively, the network that represent it would have n neurons. But because it's a rank, it's an order p tensor, I know that its rank is at most d to the p minus 1. So I know that I can represent this tensor using only d to the p minus 1 neurons. And it's easy to see, it's a simple calculation to see that this tensor will memorize approximately. Namely, when you evaluate it at xi, so you do the inner product between t and xi tensor p time, you will get yi plus minus epsilon. So you see this tensor memorizes, and it has only k, which is d to the p minus 1, which is n over d. And it's easy to check that its operator norm is square root n over k. So this proves the conjecture lower bound is tight. It proves a matching upper bound in this optimal size regime, but not in all regime. Okay, we're only in this optimal size regime. Okay, now let me go to the conclusion and mention many open problems and I think interesting directions for future work. Of course, prove the conjecture. So again, the conjecture is simply the Lipschitz constant is at least square root n over k for any k neurons, 2 layers neural network that memorizes random data on the sphere. Maybe less ambitiously, prove the conjecture for a polynomial activation in the low rank case. So remember, it's kind of funny because for quadratic, in the low rank case, we proved an even stronger lower bound. And for polynomial, we don't even know the basic law of robustness for the low rank case. And the difficulty is this matrix multiplication, type of example, matrix multiplication tensor, which shows that in general, you cannot relate the Frobenius norm to the operator norm through the rank. Now, third open problem, which I assume must be easy, but we were not able to do it. But I cannot believe this is hard, but still it's open, is to prove a matching upper bound in all regimes. So currently, in this presentation, I told you everything I know. We only know 2 regimes where we have a matching upper bound, namely the optimal size regime when k is like n over d, and then the tensor construction I gave you on the previous slides give you square root n over k. And of course, in the optimal Lipschitz constant, if you want to have a constant Lipschitz, then we have a matching upper bound because you're just using n neurons, and this is very easy in this case. Now, the fourth open problem is, of course, the more interesting direction, which is there a more general phenomenon? Like these law of robustness, you can apply them to any function class. How do you derive, a law of robustness for a given function class? Of course, the one everybody is going to ask about is multi-layers neural network, but you can also take the other direction, which I think is very interesting. What about simpler models? Could it be that simpler models, you can provably show that they don't even achieve what one hidden layer neural network would achieve? And we have already seen one example of this, which is quadratic network in the low rank case cannot achieve what non-quadratic network can do with the same number of neurons. So I think this is very interesting, both in the direction of simpler models and the direction of more complicated neural networks. More complicated models. Now, let me say for more complicated models, including multi-layers neural networks, it could be that the law of robustness is just not true. Okay, so it could be that with more layers, you can actually get optimal Lipschitz constant with optimal size neural networks. That's possible, but maybe then there is an algorithmic law of robustness. Because let me draw your attention to the fact that in this presentation, we have talked about all neural networks. We never talked about neural networks that are actually obtained by training, on real data, on data with gradient descent. So maybe with multi-layer neural network, maybe there is no law of robustness like with one hidden layer neural network, but maybe there is an algorithmic version where you can show that gradient descent will not find, small Lipschitz constant neural networks. And of course, all of this, again, tying it back to the very first slide, all of this is in the context of adversarial examples. So, of course, solve adversarial examples, but also the connection to adversarial example is not so clear because Lipschitz constant is the worst case over all points, and adversarial example is about most points. So, elucidating this connection is also interesting. Okay, let me stop here. Thank you very much.
Thank you, Seb, for the nice talk. So there's one question regarding on the geometric proof, and the anonymous attendee would like you to elaborate on the dependency issue. How do you address that?
Sure. Yeah, absolutely. So again, so for a fixed k-dimensional subspace, in most direction theta, you will have that the L2 norm of p theta is square root k over d. Okay, this is what we talked about, that you have the sphere of radius 1. When you project it, it's only a sphere of radius square root k over d in most directions. So now, if there is one such direction in your data set, where the function f has to go from -1 to +1. Okay, so you take the data point number 10 and the data point number 20. Data point number 10 has label -1. Data point number 20 has label +1. So between x10 and x20, you go from -1 to +1. So the direction x20 minus x10, this is 1 theta. So if there is one such direction in your data set which is being shrunk, then you know that you have to be square root d over k Lipschitz, because this one direction you will have to move from -1 to +1, and it has shrunk to size only square root k over d. Now, there is a difficulty because those directions that exist in your data set, they depend on p. But what you can do is, instead of showing that all directions in your data set, they will shrink, this is not true. You can choose a subspace where some of the directions are not going to shrink. But what you can show is that most directions are going to shrink. So you can look at the average of the directions, and you can show that the average of the direction is indeed smaller than square root k over d. So there must exist one direction which is smaller than square root k over d. Does this? I hope this answers the question.
Thank you, thank you. And another question is regarding on whether it's possible to make some improvements when there are extra assumptions on the data. Say, what if there's a margin condition that the data satisfy, or if the
of course. Okay, so this is I should mention it in the open problems also. It's an excellent question. So there are so many ways, so many directions in which you can take this work. One of them is, of course, to try to understand the interplay between the data and the law of robustness. So here we take it from the perspective of, we want a law of robustness for most data set, meaning with high probability with respect to a random data set. Now, in practice, you have specific, data sets. So you want to know, okay, for this specific data set, what is going to be the law of robustness there? So, from a theoretical point of view, it means you're going to make some modeling assumptions, a more precise model. Now, it's very complicated because, for example, a model that you've seen in the literature is maybe the data is produced by a small and smooth neural network. But if the data is produced by a small and smooth neural network, then of course there exists a small and smooth neural network that interpolates. So it's very hard to find the right assumption under which there is still going to be a law of robustness. Now, let me say again, it ties back to point number 5, which is maybe even if the data is produced by a small and smooth neural network, then there is no law of robustness for all neural networks, but maybe there is a law of robustness for neural networks found by gradient descent dynamics. Maybe it becomes an algorithmic law of robustness. So yeah, it's a very interesting direction.
Thank you. And another question is that it seems your result only cares about the fixed transition. Oh, well, the lower bound involves only n and k. I was wondering if you have a full-fledged transition in terms of n, k, and d.
Right. So this is a very confusing point. So this is a very confusing point because the statement of the conjecture does not make appear d. So it feels like a dimension-free statement. But it's not the case, because what matters, you have to think about what is the range of neurons that matters. And the range of neurons that matters is between n over d and n. This is a range of neurons that you need to consider. So k is always going to be larger than n over d. You cannot have a number of neurons smaller than n over d. So k is between n over d and n. So this square root n over k, even though as written it does not make appear the dimension, in fact it is something between 1 and square root d. So the dimension is in there.
Thank you for the clarification. Yeah, maybe the very last question is for beginners level, could you suggest some good exercise or resource to work on using tensors? It seems you mentioned you have a crash course.
Yeah, I do. Yeah, if you go on my YouTube channel, I think the latest videos that I uploaded, which was actually last year, is a crash course on tensors. And the paper itself, this paper, I think we explain things nicely on, what are tensors, how do they look like, and we do all the concentration bounds for these tensors in the paper from first principles. It's not hard at all, but it's not done properly in other references.
Thank you. Yeah, so that concludes all the questions. Thank you so much. Thank you again for the nice talk.
Sure. Thank you.
Thank you.
Thank you, sir.
Thank you.
Let me stop sharing. All right. Have a great day, everyone.
Thank you.
Great to
Thanks,
see you.
Joseph. See you.